So in this video, I'm going to just go over really quickly how we kind of do the generic vector addition problem. On your quizzes, there was quite a lot of issues with understanding exactly what I wanted you to do with the vector addition problem. Some people were just adding things using um, this kind of graph method, where you take a vector and you slide the other vector so it goes tail, head, tail, head, and then you just connected the first tail to the last head to find the resultant vector. And while this is completely valid for, say, making a pictorial representation of the vector, when I ask you for something like the magnitude and direction of the resultant vector, then I'm looking for the number which corresponds to the length of the resultant vector, this vector here, where you're adding g and b to get r as being the resultant vector, and b is this blue vector, and g is this green vector. You're adding these using our vector methods, our vector component methods, to find the resultant components, and then thereby finding this resultant length, and then also finding this angle r. Like the direction is the angle that this vector makes with the x-axis. And so I'm just going to go over really quickly of what these words mean. I think there's some confusion of what I mean by my terminology. So when I say what is the magnitude of a vector, I mean what's the length of this vector. So if I apply a force to the right, then what that means is that I have some vector that corresponds to my force, that represents it mathematically, and that's a 10 Newton force to the right. So if I'm doing that 10 Newton force to the right, and then I also add some 10 Newton force vertically, then what that's going to do in total is the net force, the resultant force, where the actual person moves, what the sum total of these two forces is not 20. You can't just add this one and this one because they have direction. This is 10 newtons to the right, and this is 10 newtons upwards. And so the resultant is some vector like this, which is found by using this x component and this y component as 10 squared plus 10 squared equals to r being the resultant length squared. So then you can find that r is equal to the square root of 200. And that would be newtons. So this is like square root of 2 times 10 newtons. So this is what I mean by finding the sum of two vectors. You have one vector and you have another vector, and you have to add them in such a way that you can get the resultant vector. So what I've been doing though so far is we've been talking about vectors at angles. This is an example where you don't have any angles involved. You just have a force in the x direction and a force in the y direction. So you can use these two as the x component and the y component of your resultant force. If you add this vector plus this vector, you get the resultant, but to find it mathematically of what this length is, you have to take this x component, square it, plus this y component, square it, take the square root. That's because it forms a triangle, and so we use our right triangle trick to find that out. So this is our y. So I've drawn up an example of this to try to get across the point of what we're really doing. So while pictographically you can take this vector and attach this other vector to it to find where the resultant lies as far as graphically is concerned, you can't use this to find the actual numerical values. We have to start to break each vector into its two components. So this vector, it stretches some direction out into the x direction, which is called its x component. So the amount of the vector that lies along this x-axis is called its x component. So yes, this gx is the x component. And the y vector, or the y component, is how much this green vector extends into the y direction. Y component. So if I gave you these two components, you could find both this angle, the direction and the magnitude of this g vector. If I gave you these two numbers and told you that this is the x component and the y component, you can take gx squared plus gy squared and set that equal to g squared, which is the magnitude of this direction of this vector. So, what I normally give you is I just give you, let's say that I tell you to add these two forces, one at say 15 degrees, one 15 Newton force at 10 degrees, and another 10 Newton force at 110 degrees, and I want to know like what's the total force, what's the resultant force of these two individual forces that are being added together. And what you do is you take this initial force, so let's say the 15 Newton force that's going to be represented by this G, you take this force and you break it up into its x and y components, and you separate those. So we've done this a couple times, but we can use trigonometry to break up the vector into components. So break up vector into components. And then we notice that we use SOHCAHTOA, so I know that the sine of this angle of theta g is equal to the y component divided by the magnitude of the vector. So that sine of theta g is equal to gy over g. Awesome. And then I know that the cosine of this angle is equal to the adjacent over the magnitude of the force. So this is the x component. And I can do the same thing for the blue vector. I want to break the blue vector up into its components because I can only add the two vectors by components. I have to add the y components together and the x components together to find the resultant x and y components. So that should be a b, not a g. And over b, and then the cosine of theta b is equal to bx over b. And I can immediately write these things down because I have my angles written as being counterclockwise from the x-axis. This is very important. This is how I can use SOHCAHTOA in this case. If I instead use this angle as theta b, then I'm not going to get the right sign for this cosine of theta. It's going to give me a positive if I use this smaller angle, while obviously the b vector is pointed in the negative direction and the x direction is pointed this way, going in the x direction, and it's going positive in the y direction. So the sign would be fine, but the x would have the wrong sign, and you get the wrong answer. Okay, so now that I have the two vectors broken up into the x and y coordinates, I can solve for, say, gx and gy, because in these problems I always give you what g is and what theta g. I always give you what b is and theta b. This is the magnitude of b, this is the angle or the direction of b, this is the magnitude of g, and this is the angle of g, or the direction of g. So I always give you that information, and from that you can always find the components of those two vectors. So if I try to add these two to find out what r is, I have to add this component of g, the x component of g, and the x component of b, and that gives me the x component of r. Because if you add this one and that one, then the resultant is going to be this distance right here. Let me draw that in red so it's more obvious. So if you add this component of g, the x component of g, to the x component of b, that's going to give me the x component of r, which you can kind of see visually, rx. I can do the same thing with y. If I add this component of g, the y component of g, and the y component of b, you see how these two things added together, this length is the y component of the r vector. It's the same length as this, which is the y component of the r vector, r, y. And so what I can say is, because those two lengths are the same, I can say that Rx, the x component of the resultant force, is equal to Gx plus Bx. I can do the same thing for the y direction. I know that the Ry the y value of r is going to be equal to the y component of g, the length is equal to y component of g, plus the y component of b. So you compute these two and these two from the information I gave you using the trigonometry, and that gives you the resultant of r. And then if I want to find out what r is, which is what I'm actually trying to find, I'm trying to find what is r, what is this resultant magnitude, what's the magnitude of the resultant vector of adding this force G and this force B. So what's the resultant force? What's the actual net force? So then when I have Rx and Ry, I can find out what R is. I know that R squared, since it's a triangle, we can use this triangle trick, the Pythagorean theorem. R squared is equal to Rx squared plus Ry squared. So in the notes, I use some weird terminology like I call this gx plus gy, gx plus bx, and I would call like the resultant as g plus b, and that confused a few people because they thought that they could solve for what g and b were, even though I already gave them those numbers. I already told you that g was some length and b was some length. I had a few issues on the quiz with that. So what I want to make clear is that after you have split up the vectors into their components, you add them component-wise. So you added all the x's together. All the x components of all the forces added together gives you the x component of the resultant vector. All the y components added together gives you the y component of the resultant vector. And then you can add these two vectors together by using the Pythagorean theorem. This is called vector addition. This isn't really normal addition. You can't add vectors in the same way you do normally. So r squared is equal to rx squared plus ry squared. Then you can find out that the resultant magnitude is equal to rx squared plus ry squared. I apologize for my roommates in the background. They tend to forget that I ask them to be quiet when I make these videos. So this is the magnitude of the resultant And after you've found the magnitude of the resultant, I always also want to know what the direction is. What is this angle? So normally if you knew what r, y, and rx were, and all you have to do is just use the tangent function. Because remember that SOHCAHTOA, TOA here, what this does is the tangent is equal, tangent of the angle is equal to the opposite. Opposite is ry divided by the adjacent, rx. So I can come down here and I can say that the tangent of theta r is equal to ry over rx. This is the direction again. We got direction above this. The direction of the resultant vector. And then I can take the arctangent of both sides, and this will go away. It'll leave me with just the angle is equal to the inverse tangent or the arctangent of ry divided by rx. And that is all you have to do for these problems. It seems like a lot, but really all you have to do is this, and add them together, square them, take the square root, and you get the magnitude, and then just apply the tangent function. This will be bread and butter really quickly if you just do a little bit of practice with it. I'm going to give you guys some practice next class, and then we should be ready to roll into finishing up our forces unit and going on to other stuff. But we're going to be doing this when we talk about more about forces. Also, we're going to do it when we talk about impulse, and when we talk about momentum, and probably some other topics when we start talking about electric fields and magnetic fields. We're going to have the same stuff coming up. So try and apply this to understanding of forces and any kind of concept that has a vector. This applies to velocity, to acceleration, to forces, to momentum, to impulse, to anything which has a direction to it. It's going to have vectors included. You can't get away from this. So I appreciate you guys watching the video, and I hope to see you guys in class tomorrow.